Welcome to the Rankled Engineer Podcast. Today, we'll discuss the importance of paying attention to displacement and deflection diagrams in your 3D models, as well as reviewing delegated design calculations that may not be 100% accurate but aren't necessarily materially affected. Tim's going to tell us about his trip to Germany, and I get to talk photography. I'm going to look at my single exposure of happily ever after fireworks.
Welcome to the Rankled Engineer. I'm Gates. Got Tim here as usual, and of course Allie joining us again. It's nice to see you. It's been a while. It's been a couple months since we've even thought about recording anything. It's been a crazy summer.
It was a busy end of the summer.
Yes, yeah. It seems to be the way it goes. Tim, do you have a word for us today?
Oh, word of the day. Oh, crap. I hadn't even thought about that.
I didn't even think about it either, but I got
Sorry,
you here.
I promise if I come up with something, I'll let you know.
Okay.
I feel like there was something recently that bothered me, but well, anyway.
We might have to go to the end of the show on that. But yeah,
right.
Everybody, that's the highlight of the show. So you gotta think of something. So we'll jump right in then to our code topics, or this is really less code and more structural engineering. Like, this is the root of structural engineering, in my opinion.
Yeah, this is real analysis.
Yeah, so this came about, Tim and I have talked about this many times through over the years about how important deflection diagrams are when you're doing structural analysis, specifically a 3D analysis where you're looking at all of the members in concert. And you can look at the strength and stresses on the members, but it's really the deflection diagram that tells you how it's behaving. And when we're iterating design, it's really easy to go, well, is it strong enough? Is it strong enough? Is it strong enough? But if you don't make sure it's behaving the way you want it to, who cares? You might be driving forces to the wrong location.
Exactly. Don't just go straight to the colors. You know, it could definitely be a garbage in, garbage out scenario if you do that.
Absolutely. And what brought this on for me is I was designing this tower, and it's like 60 feet, and it's just kind of a marquee. So it's isolated and standalone, 4 legs, and I had designed it with each leg pinned at the foundation, and its frames up above, and that was great. But then I got to where I wanted to work on my foundation, and the tower had shrunk a little bit. And so I went from grade beams between the columns to, I'm just going to put a mass footing in the center. And so I'm like, rather than get the individual reactions, I wanted just the overall reactions on the foundation. And so I created a node in the center and then used rigid links to connect those so that it was all fixed around the center of the foundation. I could run my analysis and just get global overturning and shear and things like that. And I ran my model and I looked at both deflection diagrams, which should be identical because analytically what was happening was the same exact thing. And my new copied one was like 2 or 3 times the deflection. And I went, okay, hold on. Something's wrong here. Not looking at stresses, but looking at the shape of it. And it turned out I had left the columns fixed on there. Or so I guess the new model had less deflection. I had left the columns fixed to those rigid links, so they were acting as moment frames rather than pinned on top of those rigid links where they would actually be able to move, rotate. And so the deflection diagram saved me, and that got me talking to Tim again about just the importance of deflection diagrams.
Right. So there's kind of an interesting thing that goes on in engineering where all of the engineering disciplines are governed by kind of some simple laws of physics, where you have like Ohm's law in electrical engineering and stuff. And our version of it is Hooke's law. And basically it says that, deflection is proportional to the force applied. And to me, once you finish putting together your model, and you look at the deflection diagram, what you're doing is you're saying, does my model satisfy Hooke's law? Does it satisfy the most fundamental part of structural engineering, which I think is a critical question to ask before you look at anything else beyond Hooke's law, because if you don't satisfy that, you don't have a model. You've got garbage, and that's really why. That's what it boils down to.
Yeah, and it just reminds me when you see somebody struggling to get a model to be stable, it's falling over. And go, did you fix it?
Instability is detected.
Yeah, they go, yeah. Well, what'd you do to fix it? I just fixed all the nodes. I fixed all the end releases. Yeah, if you have a global moment frame, you're going to get rid of those. But now, is that really what you have? Is that what you're really designing? And so,
right.
Yeah, the last project that I did, that was my issue. It just was all falling over. But I hadn't put in any lateral system yet, which was my issue. And I didn't put in a diaphragm either. So once I added a couple of those elements, it looked a lot better. And because I fixed my columns for the time being, and I was like, oh, yeah, we don't need those anymore now that I actually put a lateral system in.
And that's the difficult transition, I think, from college, where everything is a one-dimensional or two-dimensional problem, to the world of 3D, where there are simple software applications out there that look at individual elements and they take away all of the Z, and you don't have to worry about those restraints. But when you start building 4 columns and 4 beams and you're going, why is it falling over? Well, suddenly you're in the world of 3D. And if you don't have the right restraints or the right releases, things are not going to model correctly.
Right. Now there's a few layers to this. One I always like to bring up is RAM steel, which is not a real 3D program in its gravity module. It's a fakey 3D model in that it basically does everything through tributary method and then takes the reactions and distributes that to the next element in the load path.
Like RISA floor is the same, would be the equivalent.
Does it? Yeah, that one I'm not familiar with. But the problem with that is that you can actually develop stable models that call themselves unstable in that program. So you've got to know that limitation of the program to know whether or not you've run up against that, because you could be getting a very strong message from RAM steel that you made a bad model, and the fact is you actually made a good one. RAM steel's actually got the problem, which can be fine. It's not a bug per se. You just have to know the limitation of the software. If you took that same model and put it into SAP or ETABS or something like that, it would run just fine. I should have drawn a picture of it, but it's basically when you frame around an opening, sort of like a pinwheel in the sense, with four beams that basically all depend on each other. That those fall apart in RAM steel.
The gazebo where everything meets at a compression ring. Those are difficult.
Next thing is P delta. You have real life P delta where the influences of those actually iterate in your deflection diagram and actually cause additional deflections. Or does it do what RISA does, which is just does a calculated P delta, but doesn't actually send that any further downstream? SAP will actually do an iterated P delta. So if you've got like a cable style structure or something that is very sensitive to P delta, you have to know that limitation of RISA, for example, and go to SAP, which is a more intensive software as far as that's concerned. The next level would be dynamic, modal, that sort of thing, where things are actually flopping around and moving in various modes, either individually or in concert. Individually would be more simple, and ETABS and SAP are excellent at that. And I'm sorry for the ones I'm leaving out, like STAD. STAD can also do this sort of thing. But if you look at like first mode, second mode, third mode, those should also make sense to you. And it really behooves a structural engineer to learn what the various modes look like. And if not just the static deflection diagram, but if the modes don't make sense, you also still don't have a model, because those should be speaking to you correctly also. It can really tell you whether you've got a good model or a bad model. And then the last one would be where you apply a time history analysis to something, and you get to see a real earthquake on your building and watch some crazy jiggling and that kind of thing. And the performance-based design. I've seen that done as a method on some towers here in downtown Los Angeles, for example. And I've seen all the other forms of deflection diagrams work, but that one didn't work. And I'm like, you still don't have a model, kiddo, as I'm helping somebody else with this. So it's good to know that the strengths and limitations of all the different types of deflection diagrams that there are out there as well.
Yeah, absolutely. And it takes time. I think it's when we're looking at a beam that bends, that college, you learn that and you figure out how things move and deflect. But when you start getting the spaghetti models together of all of these beams that now have uplift, vertical down, shear in the X and Y or Z, it takes more of an eye to really pick, well, why isn't that node moving? Like, why is it stuck? Or why is there no load getting driven into this frame over here? Is it because it's more flexible than the rest, or is it because it's not attached to your diaphragm or some other load transferring element? And so Ali, you're quite a bit younger than both of us. So so how do you feel about
decades younger?
Yeah, and congratulations for passing the California exams.
Thank you.
That is awesome. Go out and use the surveying modules that you studied for.
Those were the worst.
Wasn't it the worst?
I only wanted to pass that so I would not have to look at the material again and take it again.
And anybody who's taken the exams in California has been there with you. So in your youngest kind of career that you've got going on now, what do you feel that this is something you have a grasp on? Is it something you need to work on? What are your...
No, I don't have a great grasp on it. Because I haven't touched a lot of big projects that require a full model until recently. So it's been a lot of like piece calcs to get there and hand calcs, and then switching Teresa and putting things in. It's like, all right, I have to figure out all my boundary conditions. And then it took me a while to figure out stability and deflection. So then anything that you guys talked about past that with modes and time history analysis, like I understand, like I shouldn't say understand it. I know it that it's in ASCE and they reference it, but I don't think I've really ever used it or have.
Well, that's important. And if I were talking to you as saying, you're about to put together your first 3-story freestanding steel stairway, for example, which is something that a lot of engineers end up working on. And let's say that you're in a part of the world with no earthquakes. They might just say, why would I look at modal analysis? And the fact is, it's very easy just to click the modal button and click go. It's maybe 1 to 2 clicks. It's so simple. And when you do, you get to watch your building do something that demonstrates how it's put together, whether or not it's actually going to see an earthquake at any point in its life. It basically proves when you do that you built a good model, so that you can trust the way that you assembled all of the hard parts of the structure. It doesn't demonstrate anything about the loading. It demonstrates everything about how you did the end releases, the torsional releases along the lengths of the members and that sort of thing, and just the material properties and the types of members that you put in together all around. Even whether you oriented things correctly, in some cases like single angles, you'll be able to see them do their thing in the right direction if you oriented them correctly. So that's why I would say, even with things like that, which you've done steel stairways and that sort of things before, because those tend to hit all of us at some point. It should look right, and it's really important to get to know what right looks like, I think.
Yeah, stairways. So I got some texts from Allie like 6 or 8 months ago, and then I think it was like, this is a phone call, because she was working on stairs in RISA for the first time. Yeah, and she's like, it doesn't work.
I was like, I don't get it. I don't understand.
As soon as you go diagonal and go from two planes of orthogonal structure.
Yeah, it starts doing weird stuff.
Yeah, because it becomes a compression strut that's trying to hold up the
whether
floor
you want
above
it to or not.
And so, but you can release it axially up at the top to keep it from getting pushed down on. And there's lots of tricks. And that's, since you're dealing with boundary conditions and end releases, there's two ways to get the same result. You can either mess with the member, or you can mess with your reaction point.
Connection.
And so that makes it even more confusing, because you got to start keeping those two things straight. Where I find it a lot is, surprisingly, I do model some pretty large structures in wood in RISA, and they have pitched roofs that have a severe enough angle that I can't just treat them as flat. And when you bring that rafter down over the eave beam, if they're in the same plane, well, now you're locked in with the bending axis of the joist into the beam, and that's no bueno. That does not work really well. You start twisting a lot in that eave beam and blowing it up in shear, which is a check that's easy to miss if you're only looking at bending unity. If you don't ever look at your shear diagram, I found that shear diagrams are great ways to see what kind of axial strains you have going on that wouldn't show up in a bending calculation. So you have to offset it a little bit, put a little rigid link, and run it over the top so that you can get that pin action, but still get the vertical and shear going on at the eave beam. So it is, like I said, I think it's the most fundamental portion of design, making sure we have a nice, valid design, but it's also the most difficult thing to master as a structural engineer. And it's not like they give you on the PE exam, here's a deflection diagram, what's wrong with it, or what are your observations? So it's difficult to without like interviewing somebody on the spot to really understand how they.
Closest thing I've ever seen is in tests that an employer may give you as you're applying for a job. They've said things like they'll show like maybe a tall bay and then a short bay that's attached to it, and then put a point load or 2 point loads. You only need one really to make the point. And then they say, please draw the deflection diagram. And I think that's a very smart question, because it shows that you understand, relative rigidity, because they even gave you the EIs and stuff like that. They show you you can show relative rigidity. You can show that, a moment connection is 90 degrees, no matter how you rotate it, it's always 90 degrees. And it should look like that when you're done drawing. And, you got to take it up in other places and things. So I think those make a lot of sense. And it's the only place I see stuff like that is those kinds of tests.
Definitely. Well, kind of dovetailing into this kind of a second subtopic came about because I was reviewing some shop drawings and delegated design calcs, and the end result was correct. The material selected, the sizes and everything was adequate, but the inputs were wrong. And of course you might say, how is that possible? And what it is that the inputs, while they were incorrect, didn't materially affect the end result. And it was things like using the HSS steel strength of 46 KSI instead of the pipe steel 35 KSI. But bending stress was at 20 or 30%. So reducing by 50% or a third of your bending strength wasn't going to cause that to fail. But then it was also like the bracing along this pipe element was incorrect. It was stated to be continuously braced, even though it's not, but a pipe section's not really prone to lateral torsional buckling. Like, it's not normally not the primary mode of failure for a closed section.
No, compressive buckling, but not lateral torsional.
Yeah. And so I was going through this and I kind of called Tim and I'm like, I know it doesn't affect it materially, but when it can be right, it should be right. Like, to me, that's an expectation that you should be. And then there's times when you just don't know if it's going to affect it materially or not. So how have you handled the line between, it really happens on delegated engineering, where you're not the engineer of record over it. You're not assuming responsibility, so you're kind of critiquing the work, but you're also kind of at arm's length from it. I know some people just check the inputs, make sure that they got the right loads and the right geometry, and they're like, well, I'm done. Everything else is your responsibility. So do you turn a blind eye, or do you sit there and mark it up in red? What are your methods?
Depends on how much time I have. I definitely, if something needs to keep moving and I can verify that it works when you do it right, I send it forward. If I'm also able to, I will ask them to correct their inputs, and if need be, their processes. The classic one with me is people grabbing the 1989 steel manual and designing it according to the old Green Book ASD approaches, which I've done and I know and I'm familiar with and I understand and I trust, and it's not the law. And I want, if I'm representing a client who's buying something that is supposed to be designed according to current legal standards, that's what I'm going to get. And that's why I ask for it.
Absolutely. And the Green Book is great because it has information in there that they just have not reprinted in later editions. And so I understand why there's like beam tables and stuff in there that they don't reprint anymore. And so it's this great resource, but then it's like, they never want to buy a new version of the steel manual and realize that the bolt strengths have changed and weld values have also changed. And, it's great as a kind of a quick reference for those things, but you really got to be to the current code. Allie, any of your delegated experience?
I would say I typically overmark things up than not. Like if the inputs are wrong, like a lot of times I'll still see like 90 mile per hour wind, right? Which you're like, that's not to today's code. So I'll mark those up just like, at least it's a CYA, like, we don't need our liability on that. And I've also had steel design where there's like no real calcs for it and they're pulling from an old book, which I have never seen. So it's like,
sorry,
I can't verify. Please redo.
All three of us have been owners reps. Been the subject matter experts for an owner when it comes to structural things, and I think that's where I've really honed my skill at looking at designs, whether they be from the prime consultant or a delegated design. I did it at Duke Energy. I did it at Disney. And the nice thing is you have a little bit more kind of carte blanche authority when you're the subject matter expert for the owner, because you can say, this is our standard and this is what we do regardless of the code, as long as it's more than. And so that gives you a little bit more of a position to push back and say, we want it done correctly. And the reason that I feel it's so important in those kinds of environments for an owner is that this isn't the last time someone's going to look at these calculations or this design, because there's going to be a remodel, there's going to be a change, there's going to be some kind of infrastructural need to come back to these calcs. And if your baseline information is wrong, you're handicapping the engineer who's coming behind you, who's going to say, oh, they used 500 pounds when really it was 640 pounds, or oh, they must have used HSS steel because they're using a higher grade in the design. And you don't want to have a cascading effect of them relying on bad information to make a new design that maybe doesn't have the fat in it that was there.
At Disney, for example, the project isn't done with the building until the building is demolished. It's basically an ongoing project, even if there's 8 years, 15 years, whatever between phases. The fact is, you're just picking it up and moving it further forward. So, yeah, it is important to not let the next round of engineers second guess the engineering that was done for it. Which is why you want to have the paperwork in order.
and at Duke, it was substations where it was what I was in, and we were constantly swapping out new equipment. And the thing I've learned about equipment is it seldomly gets lighter. For some reason, it gets more efficient, but it does not get lighter. And so, we wanted to have good design drawings, good calcs that we could go back and rely on. And I remember I was sitting in a meeting, and it was a lot of locations, and it was kind of the same kind of installation at each location. And the design engineer was, as Ali was pointing out, using 90 miles an hour wind, except for rather than using 90, he was using the correct wind speed, but he was multiplying by 0.6 twice, both on the front end and in his calculations. And I kept pushing on this, like, it's not correct, even though it did not materially change. It was FRP, it was plastic design, right? It was fiberglass elements, and there was this great resistance. And one of the guys after the meeting kind of said, he's like, I don't understand. You're the owner's rep, and all he's asking you to do is correct the math, and this problem gets laid to rest. But he was pushing back on it. He's like, it seems like a really simple. I'm like, he thinks he's right, so he doesn't want to do it. But if your owner's asking you to do it and it's above and beyond, just do it if it's simple. And depending on your contract, it may be billable, right? So if it's a change order, I don't think this one was, but it just gets you into, it's weird territory when you have people pushing back and you're the owner.
Yep. I have another deflection thing to bring up. Deformational compatibility. This is something where it comes up when you're attaching new buildings to old buildings, or when you're doing something that can modify the rigidity of an existing element or something like that. In one instance, I was working with an engineer who was designing a ride system that was bearing on my facility, and he basically provided me with loads and anticipated deflections. I remember in one particular area, he had the structural model. He was bearing in the middle of a 24-foot long beam. He was applying a 5,000 pound load. And he said, and I expect you to deflect 0.004 inches. And I said, and what precisely would you like me to make this beam out of? Because I don't think we have anything on Earth that can do that. And I sent him that, and I don't know. It was very strange, but ultimately he was in Canada. He ended up at my desk one morning, and he said, all right, Tim, we're getting to the bottom of this. I'm like, you're damn right we are. I don't know what you're thinking. But it was basically the unifying thing between us was I mean, that if that's not Hooke's law, I don't know what is, right? It's force and deflection. So that's basically how we talked to each other was by what we expected in terms of each other's relative deflections. So that it's another reason why deflection can be so important. Something that engineers only usually think about in terms of acceptability criteria. Do you meet L over 240? Do you meet L over 360? Things like that. But it can go beyond that, definitely.
Yeah. So my favorite deflection compatibility story, I'm going to steal it because it's Tim's. Tim has told me this one. Okay. I'm going to steal it from you.
Maybe I'll recognize it.
You will. Oh, yeah. So there was an existing flat strap X-brace, and the architect wanted to put a door through it. And so rather than designing the system for strength, Tim designed the portal frame that attaches to the flat strap bracing to match the deflection of the brace as if it was still there. If that's not beautiful,
strong enough for the force that was going into it.
If that's not beautiful engineering, the building does not notice that there's a door where there used to be a strap, and it's all because of deflection. I get the story right? Yeah, because that's a beautiful story.
That's perfect, and I really love the idea that you use the term "does not notice," because that's the way I always explain it. If you can do something to change a building, but it doesn't notice that you changed the building, then you did a good job.
I still want to be there during an earthquake to see the door kind of like,
right. I can't remember if they actually went through with that one or not. Maybe they did. Maybe they.
But when you're an engineer, theory is as good as constructed.
Yeah, true.
Well, awesome. So I appreciate that. I think that was a fun discussion about.
Oh, I'm flattered you remember that.
Yeah, of course, of course. You didn't tell you alluded to your finger of God story of an individual modeling a tower that was restrained in the middle of its height.
I didn't quite get to that.
Which is
that tower in Los Angeles, it was moving beautifully, but it was as though God was holding on to the 25th floor somehow of a 54-story building, and everything was moving fantastically. But I'm like, who's doing that? So I was asking him, I'm like, how is that working? I have this whole tower doing what it's supposed to do, but God's holding on to the 25th floor somehow.
Which would
he
be
eventually
a good ally.
Figured it out.
Yeah,
it was surprising. It took him a while to figure it out. This was back in the Wild West days when we hooked 4 computers up to each other just to get enough computing power. And this is not that long ago. It was 2004, and
it's a long time ago to Ellie.
It was after that. It was more like 2007. Anyway, we hooked multiple computers up to each other. He would hit run, and then he would go home for the weekend and come back on Monday because it needed a full 48 hours to run, just to get enough calculations to be able to do that. And I'm not like laughing at the inadequacy of their computers or anything like that, because I realized how much was involved in that diagram, because they were deflecting so many little parts and pieces to make that work properly. It was pretty amazing, actually.
And you start doing p deltas and deformations, and then it's calculating that same part 10 times.
It has to iterate
before it, asymptotes on the graph, and they're good to go.
Stabilizes or doesn't.
Come in the next Monday and it didn't run. That's when you really.
And it's on the ground. You're like, oh no, the computer's on the floor.
Well, Tim, you just one of the reasons we haven't been together for a while is you just took like a huge trip to Germany.
Oh yeah, that's true. I was in Copenhagen first, and then Berlin, and then Amsterdam, and it was really interesting because I never saw myself ending up in Copenhagen for any particular reason, and we just did because the people I was with wanted to go. Something that was kind of funny about that was going to Tivoli Gardens, which was a place that was really impressionable to Walt Disney when he was looking at the Disney parks, or Disneyland, early on. And I couldn't help but try to see the things that he saw when I was walking around, to try to take pictures of like, we should do this, we should do that, kind of like what he was thinking in 1950, whatever it was, 3-4, whenever he was there. It's an amazing place. They had one wooden roller coaster there that's been running since the 1800s, and it's all covered in rock work. So it's all kind of a mountain-based kind of thing, and it's like, that was kind of lifted from those. Yes, it is. And various other things. There was a gigantic whale face with a big whale mouth that I took a picture of. I'm like, well, that looks familiar. 1956. And also, they were really famous for all the little lights that trimmed the sides of the buildings, like you see on the main street in the parks, and those are even known as Tivoli lights to WDI. That's what they call them when they're talking about those types of little light bulbs that trace the edges of buildings. So it was just sort of neat to see the origins of all that too. So. That's I don't know. Cool. Saw interesting stuff where I was going. It always gets you to rethink America whenever you go to foreign countries.
Did you get to drive on the Autobahn?
Not this time, unfortunately. I love doing that. Man, last time I was in Germany, I was flooring it for distances. It was great. I had people asleep in the back seat, and I was like leaning over. I'm like, I'm going 135 miles an hour. I love that kind of stuff.
Yeah, beautiful.
But no, not this time. Turns out that Oktoberfest was canceled this year by Germany, by Bavaria, whoever did it. So we had altered our. We were originally going to go down to Bavaria, but instead we went to Amsterdam, where I had been before. But Amsterdam is fantastic. It's just so it's got to be one of the prettiest cities on earth. So it's just so amazing to see.
Yeah, the only thing that disappointed me with your trip was you didn't tell me you were going. And so like I'm texting Tim and no responses for like a
and
week.
I'm not answering.
And
what's happening?
So I texted somebody else that we'd worked with in the past. I'm like, is Tim dead? Or, you know, what happened to Tim? And he's like, oh, he's in Germany for like 2 weeks or something like that. I'm like, okay. And one of the things that I texted you is what I want to talk about next is I texted you this picture of fireworks. And I was like, I'm going to get an immediate response from Tim on this one because he's going to love it.
Silence.
And I'm like, all right, that's the last straw. I got to find out where Tim's gone. And so then when Tim got back, I'm like, all right, what's the last text message you got from me? And then I kind of was like copy paste.
Scroll backwards.
But I feel bad because I probably should have just kept going for the duration because then I could have remembered what I had to tell Tim, you know, because it's so life critical that I tell Tim so much of this stuff. So I wanted to talk about this picture. You saw the picture, right, Allie?
Yeah.
Probably. Yes.
The happily ever after in one exposure.
Oh, yeah.
So what did you think of that picture?
Was that the really pretty one?
Yeah, it was one of all of the fireworks. I thought you had seen it, but
I probably did. Was it on your Instagram?
It was.
I did see it. I did. I liked it a lot. I thought it was a great picture.
What did you think of it, Tim?
Amazing.
I want to know where your mind went though when you saw it, because
that's an interesting thought, because I have seen Disney fireworks. I worked on Main Street in the Magic Kingdom for years. I can't tell you how many times I've seen, you know, Disney fireworks shows. Even when I was at Disneyland, Fantasmic was right in front of where I worked for years, and just seen so many. Which means when something comes along that makes it different, you know, where I can show me all of them at once.
What surprised me, well, so I guess we'll backtrack. So this is something I wanted to do for a long time. And Josh, who is the chief photographer at Disneyland, which Tim and I agree is like the coolest job title in the world.
Yeah, but he does such an amazing job too.
Yeah, right. But to be the chief, right? That's just awesome. So on the Disney Parks blog a few years ago, he posted a shot where he did the same thing with the Disney fireworks at the time, and it was Remember, I think, was the show. And the nice thing is he gave his settings, so it gave me a starting point of where to go with it without having to do a lot of legwork. And so I set off, as it was like 2 weeks prior to Happily Ever After and Epcot Forever ending. And so I had kind of a game plan. I'm like, I'm going to shoot Epcot Forever, get my bearings. And I'm going to do Happily Ever After, and then I'm going to come back and redo Epcot Forever, assuming that the first shot wasn't going to be perfect. And so that didn't work out. Things happened so I ended up at Magic Kingdom with my wife and son, and the opportunity to shoot single shot of Happily Ever After. One of the things so the setup is, it's my Nikon D750 with the stock 35 to 120 lens on it, or 24 to 120, and it's set up at about 40 millimeters because I wanted to get pretty much all the pyro, and it's pretty tall, and I was set up about a third of the way down Main Street so that I could get the nice wide view of it. And then I had to put an 8-stop neutral density filter, so it's a really dark filter. You know, it's like made for taking pictures in bright daylight that you want to capture like water moving. So you can't see anything out of the lens. So you have to change the filter to 1 stop, get it all framed, and then flip it back, push the ISO all the way down, put your aperture like almost all the way up. It was like an F18. And then you just hit go. Like you just use your little stop to keep the shutter open for 17 minutes or 22, whatever long the show is. And one of the things that Josh had mentioned is that he used noise reduction inside the camera to, you know, as the sensor's on for 15 minutes, it tends to get warm and then give you hot spots. And so that allows the camera to process it and reduce some of that. But I'm like, I can do that in Photoshop if I need to. So I turned that off because he's like, it took like 15 minutes for his photo to process and write it to the SD card. And we had planned on as soon as Happily Ever After was over, was booking it to Epcot to shoot.
You're on a schedule.
Yeah, to get, we had like an hour and a half to get there. And so I'm like, I'm going to turn off noise reduction so that I don't have to worry about that processing time. But I still expected after 17 minutes for it to be a little bit of time before I saw the image. As soon as I closed the shutter, the image popped up because it didn't have to do any post-processing. And I was like, oh my goodness, it worked. Like, I couldn't believe that I had captured this shot. And there's a little bit of tweaks I would have done if I'd had the opportunity to shoot it again. But it was like, well, that's pretty, let's run. So we ran to the monorail, and then I was looking at it on the monorail, and I'm like, that's exactly what I wanted. And after studying the photograph, what surprises me is how symmetrical the show is. Like, there's lots of asymmetrical...
How well balanced it is. Even though they come from the left sometimes, they come from the right sometimes, but when it's all said and done...
Yeah, it's pretty even, the launch platform.
But when you think about it, it's because they lay out the equipment really equally. The boxes, they're all fully loaded, and they've launched, some of them early and some of them late, but ultimately they all get launched.
And even the aerials in the center, you're like, that's pretty even spread. And granted, it is such a truncating of light. You're really seeing the bright parts of the explosion and the bright trails.
What was the wind like that night?
So actually, I lucked out on the wind. I think at MK it was pushing mostly back, so you got it cleared the field of view. Whereas at Epcot, it was dead enough that it started to glow a little at the end.
Yeah,
but especially with the finale of Epcot shows, right? Mm-hmm. They're always just massive.
It's a lower show also, so it get more of that ground effect.
Yeah, absolutely.
I don't know a lot about photography, but how do you do it so not all the smokes?
So that was, that's always a challenge, and that's where I think the wind was helping me. The wind was not static. But it wasn't. It's always bad if it's blowing towards you.
Yeah.
If it's blowing to the side, you can on shorter pictures where you have more light coming in, you can often see the side. You'll see a firework here, but a smoke trail next to it from the previous launch.
Mm-hmm.
So I think the predominant wind was more northwest. And so it was clearing the smoke pretty well, but it's such a long exposure, and the castle's not quite as bright as I would like it to be, that you're really only seeing bright points of light. You're not seeing even the glow of the clouds or the smoke, because the camera can't pick it up. It's so dark. Like I said, you look through the viewfinder, and it's just black.
Nothing.
You can't see anything, even with the castle illuminated. And so I'm excited to try some of these techniques on the new shows. I've only seen Harmonious live. I haven't seen the new MK fireworks, but
whenever I was going to Epcot to watch Illuminations, which I saw there, I think 50 times is probably conservative because it was running a long time.
98, 99, yeah.
When I would be walking around before the show, I would say tonight's a Morocco wind, or Germany, or Italy, or something like that, basically meaning the smoke is going to hit that country. And then I would basically make sure that I was somehow mostly the opposite, if not completely the opposite of that. But yes, it was the place where you didn't want to end up. So yeah, that was always my terminology. Like, it's a Great Britain wind tonight. That's where you don't want to be. That was always my thing. And people who've been to Epcot with me to see that show would know I always kind of mumbled that to myself before the show.
Awesome. No, that's so. Yes, I'm very proud of it. I'm a humble photographer. I'm not a super photographer. So to get that shot, I was pretty excited. And
you said that guy's name was Josh. I'm trying to remember.
Josh Saduk. I'm not quite sure how to say.
Did you ever meet him?
Tim and I have talked. We're not much for celebrities, but there are certain people that are
celebrities to me. Yeah, that's what I call them.
And I saw him a few times in like the lunchroom, and we worked in the same building. He was on the 4th floor. We were on the 1st floor, and you'd see him, and you're like, I want to talk to him, but do I want to be that guy that's like, I know who you are. You have no idea who I am. And so I never did talk to him, which is I kind of regret. I think that would have been a fun fun conversation to have. But
Yeah.
you know, I'd see him walk around. I'm like, I know who he is. I know what he does. You know, for a while. So one of my big mentors and friends is Ken Estes, who to me is the quintessential structural engineer at Disney. And there was a while where I knew who he was and he didn't know who I was, but I'd like see him on the tram at Disneyland and I'd be like, oh, do I talk to him or do I not? And now I text him like once a month or once a week, and it's like, it's nothing. So meet your heroes early. I don't think you're going to get disappointed, but you know, especially people that are in your industry or doing things you like, talk to them. The worst they can tell you to do is go away.
Yeah, which is pretty rare, honestly.
People like to talk about themselves.
The people at Disney who I talked to, who I knew were kind of like, you know, involved in projects that I really liked in the past and stuff like that. You know, always happy to talk about it. They're always nice about it.
You just have to have something interesting to say. That's all it takes.
Yeah. Yeah, I think I always tried to come up with something to say first. Yeah.
That's the only trick. You gotta have that ready to go, locked and loaded, so that you can spit it out. Awesome. Well, unless there's anything else, it's all good stuff. Thanks for joining me. It's been a while, Allie. Excited to see you, and Tim, glad to have you back in country.
Thank you. I made it.
Well, everybody have a good one. This is the Rankled Engineer. Bye, Allie. Bye, Tim.